Let's discuss how to find the arc length of a curve. So we've found the arc length of a circle before. That was back in trig when we looked at radians. Radians directly give us a comparison or a way to find that arc length. S is equal to theta over r. If we think about a curve though, we've never found the length between 2 points. So if I have these 2 points, we don't know what that length would be in there, this length in here. We've found the length of straight line paths. So if I have a straight line, and I know that this is a point x1, y1, I have a second point x2, y2, well then we found the distance between them, or the length of that straight line. It's equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. Or another way we can think of it is the change in the x's squared plus the change in the y's squared. We're going to use a very similar approach to this bottom one to find this arc length. What we can do is we can think about this curve as a lot of little tiny line segments. We're going to use an approximation the same way we used to approximate the area under the curve. We said, hey, we have an area under a curve. We don't know how to find that, but we can put a bunch of rectangles in there, and then we can say the rectangles are a pretty good approximation of the curve, and that gives us an idea what the area is. And then what we said is the more rectangles we take, the more accurate our curve is going to be. The more and more we have, the smaller those rectangles, the better our approximation becomes. So maybe here I start off with lines, these green lines. I'm trying not to draw directly on top. If I draw 4 of them, you can see it's not perfect. We're a little bit under in certain parts. I'm trying to hit my curve, but in certain parts it'd be a little bit under. And then certain points it might be a little bit above. But the more and more lines I draw, the more and more accurate this thing is going to be at approximating the actual area under the curve. And so that is going to be our idea. We are going to take this curve and to draw a bunch of lines on top of it. Sorry about the plane going overhead. Alright, so let's think about this. Let's get this a little bit more formally written down. We want to find the length of this curve generated by y equals f of x from a to b. We first must state that f of x must be a smooth curve. It must be differentiable. That is the key. If we're going to do this, it has to be differentiable, so it has to be a smooth curve. We're going to break these a to b's up into partitions, the same way we did with the rectangles for our areas. The reason we're doing that is because we're going to find out all those individual line segments' lengths. So a is equal to x naught, less than x1, less than x2, all the way up to xn, which is our terminal position b. Then we're going to find yk, which is equal to f of xk, so that we can find that point pk equal to xk minus yk is a point on the curve. We can connect pk minus 1 and pk using the straight line where delta xk is equal to xk minus 1, and delta yk is equal to yk minus 1. Simply the change in the x, the change in the y between 2 points. These are just points, 2 points along our curve. And then we can find the distance between those 2 points, the same way we did just a second ago in our linear case. The length of that curve between those 2 points is simply our distance formula. It's the change in x squared minus, or rather plus the change in y squared. It should be a plus. We can approximate the length of the curve then by adding all those areas up. This is looking the exact same as what we did with our area under curves. We're just now doing line segments. We're doing a bunch of lines, adding them all together to give us the area, or to give us, the length of this curve. The approximation improves as the number of partitions increase. And so in order to take the limit, we have to use the mean value theorem because we need to express our delta y's in a slightly different way. So we can say there exists a ck in this interval xk minus 1 to xk, just in our partition, such that the change in y is equal to f prime at that point times the change in the x's. So this is just the mean value theorem, or a summary of from what we saw in Calc 1. Therefore, putting this all together, we're driving the norm of the partitions down to 0 of our lengths. That is saying we're taking the limit as n approaches infinity of the summation k is equal to 1 to n of the square root of the change in the x's squared plus the change in the y's. The change in the y's we've just written in terms of this mean value theorem, and that's equal to, then we have the still the limit k is going from 1 to n. Notice what we can do is, because we have x delta xk in both of these, and they're both squared, we can factor out that bit and highlight, and we can take its square root, meaning we can bring it to the back here as just a delta xk. What we're left with inside is we factored out this first delta xk, that's just a 1. Then we factored out the next one, that leaves us the f prime ck. And now this is looking just like our integral. We're taking the limit of summation delta xk. Well, we can write that as the integral from a to b of the square root of 1 plus f prime of x squared dx. And that gives us the area under the curve, the arc length of the curve. I keep saying area because I am relating it back to the area, but it gives us the arc length of the curve. Y is equal to f of x, provided that our f function is differentiable and that derivative is continuous from points a to b. And then we can find that limit by simply taking the integral from a to b of the square root of 1 plus the derivative squared dx, which we can also write that, didn't need to write this 3 times over, that middle one shouldn't be there. We can also write that in terms of the dy dx's, doesn't matter how we choose to express that derivative. So let's take an example. Let's see how to put this all together. This is really very formulaic. As long as we know this formula here, it's very, very simple. And so let's find the length of y is equal to x to the 3 halves from 0 to 4. I should say x is equal to 0 to x is equal to 4. All right, so what we need here is we need the derivative of the function, and then we're going to have to set up our integral. But first thing we need is the derivative. So let's find the derivative, y prime, or if we want to think of it as f of x or dy dx, however we want to express it. We need the derivative of that equation. Dy dx is 3 halves x to the 1 half. All right. And the other thing I like to do is we are going to have to square. I think it's sometimes easier just to square before we put into our integral. It just makes it a little bit easier. So if I square it, 3 halves squared is 9/4. X to the 1 half squared is just x. And we're going to be doing sort of similar things in surface area. And so for that reason, I do think it's sometimes easier to find both of these things outside of the integral. Don't try and do it all in the integral. Find those first, and now let's set up the integral. So we're integrating from 0 to 4 of the square root 1 plus 9/4 x dx. So our antiderivative of this, we would have 1 plus 9 to the 9/4 x to the 3 halves power, because we're down to the 1 half power, means we need a coefficient of 2/3. But the other thing is we have that slight chain rule here where we have an inner function as well. We have that 9/4 x, so we'd have to, if we're to take the derivative multiplied by the 9/4, that means I also need to multiply by a 4/9 to get rid of that. We could have used u substitution. We could have said, let's let this represent u, and then we would have gone to the same point. But remember, with these easy chain rules, I think it's just as easy to go ahead and do it in your head. So we're evaluating this from 0 to 4. Let's go ahead and simplify and plug in. So 2 times 4 is 8, 3 times 9 is 27. 1 plus 9/4. So then we have the 4 to the 3 halves minus, keep this in brackets for right now. So when we simplify this, the 2/3 times 4/9 is 8 over 27. And we're going to go and plug in. So we'll have 1 plus 9/4 times 4 to the 3 halves. Let me keep this in brackets. Minus 1 plus 9/4 times 0 to the 3 halves. So notice that last term is not just going to zero out. We do have that 1 there. So we have 8 over 27 times, this will give us 1 plus 9, which will be 10 to the 3 halves, minus 1 to the 3 halves, which is just 1. So not going to give us a pretty answer. We'll have 8 over 27 times 10 to the 3 halves, which doesn't have a nice clean answer, minus 8 over 27. And so there would be our arc length, L. There's our arc length. So that was pretty straightforward when the function was defined in terms of x. We had an equation y is equal to x. But like we saw with our volumes, it can be challenging sometimes if an equation is defined in terms of the x. X is equal to something in terms of y. So what if the function is in terms of y? Well, we're going to need a different arc length formula then. So what if we have the curve x is equal to, we'll call it g of y just to give us some difference here. So a different function, x is equal to g of y. So the function is now defined on y. We have a function x on y. So provided that g prime of y is continuous, same as before, we have to have that possible. And let's change our points around a little bit, again, just so we don't confuse ourselves and think that it works for the same x values. So we have I really need this to be my g of c, and this will be my input of c. And then we'll have 2-point D, where again our x is the output given the input of D. Oops, need to get rid of that. And that should say is. So then the length of our curve will be the integral from C to D of 1 plus, this will be g prime of y dy, which is going to be the same, I don't need this middle one, as if we used our dx dy notation. Dx y. And then this is now a dy. So it's the exact same formula, it's just we're doing everything in terms of the y now, but it's otherwise exactly the same. Let's take an example here. Let's say we want to find the arc length of the curve x is equal to y to the 3 halves divided by 3 minus y to the 1/2 from y is equal to 1 to y is equal to 9. So again, if it had been relatively easy, like that first function we dealt with, the first example, we could have just solved that for the y, and we could have used the same formula. But here this is a much more complex formula, or a much more complex equation that I don't want to have to try to solve for y. Don't even want to bother. And everything's in terms of y, so I'd really like to just be able to use a thing in terms of y, and so we will. We're going to use our formulas here. So the first thing I need, once again, is that derivative, dx dy in this case. Try that again. That needs to be, yeah, the dx dy is good. And so we take the derivative of this thing, we multiply the 3 halves to the front, we get 1/2 y to the 1/2 power minus 1/2 y to the negative 1/2 power. And so then when I square that, might be easier to factor out the 1/2 first. I'm going to show a couple extra steps on this one, just to make sure we're all comfortable. So I'm going to take this whole thing and square it. I factored off the 1/2 first, because then I just get a 1/4, and then I have to FOIL this other thing out, so I get y to the 1/2 times y to the 1/2 is just y, minus 2, because y to the 1/2 times y to the negative 1/2 is just 1, and then there's 2 of them, plus y to the negative 1/2 times y to the negative 1/2 is just a negative 1. And so there is my derivative squared. So let's go ahead and set up our integral. We were integrating from 1 to 9, or we're finding the arc length from 1 to 9. We have the square root of 1 minus 1 plus. Our equation, we had 1/4 y minus 2 plus 1 over y dy. And so let's think about simplifying some things in here. Well, we have the numbers, or the constants here. We have a 1 and we have a 1/4 times -2. That's a -1/2. So that would give us a 1/2 plus 1/4 y. Better yet, let's do this. Let's turn that 1 into a 4/4 and then factor out the 1/4. And then this, I'll deal with that in just a second. So we'll factor out the 1/4, so we'll have 4 plus y minus 2 plus 1 over y dy. And now the square root of 1/4 is 1/2, so I can bring that 1/2 to the front. I can simplify the 4 minus 2, that is 2 plus y plus 1 over y. And that is still under the square root. All right, so now what we'll do is let's get a common denominator. So we'll have 2 over y, 2y over y, plus y squared over y, plus 1 over y. And we have our dy out there. And so if we think about this as a polynomial in the numerator in descending order, we'd have y squared plus 2y plus 1 over y dy. So what I can do is I can factor the numerator now. Y plus 1 squared over y. And that allows me to take the square root of the numerator, which is helpful because when everything was inside that square root, really didn't have much I could do with it. But once I get that y plus 1 out of the square root and just have y plus 1 over the square root of y dy, well, now let's try some substitution. So let's let our u equal the square root of y. That means du is equal to 1/2 y to the negative 1/2 dx. And in case we need it later on, I'm going to go ahead and solve for both my dx and my, that shouldn't be a dx, that should be a dy. I'm going to solve for both my y and my dy. So y would be equal to u squared. And then dy would be equal to a 2y to the 1/2 du. So let's make those replacements. We still have our 1/2 in front. Let me stop writing the equal sign for a minute too, because I'm going to treat this as a definite integral. I'm not going to change the bounds over yet. We'll think about it. So indefinite integral. So just leave it as an indefinite integral. We're going to have u squared plus 1 over, and then our square root of y we said was just u, and then our dy we're going to replace with 2y to the 1/2 du. Well, we just said that y to the 1/2 we called u. So we can write it as u squared plus 1 over u times 2u du. And so the 2 times the 1/2 cancel, the u's cancel, so we're left with the integral of u squared plus 1 du. And so now when we take our antiderivative, we have 1/3 u cubed plus u, but I'm going to replace this with my, let me stop calling it equal. So now our definite integral, we can go back and calculate the definite integral of this thing. We're thinking about the original 1/2 from 0 to 9, or was it 1 to 9? 1 to 9 of y plus 1 over the square root of y dy. That must be equal to 1/3. I replace my u was square root of u, square root of y cubed plus square root of y. We're going to evaluate that between 1 and 9. Let me fix this real quick. That 1/3 needs to be directly with the cubed root of y, because the 1/3 was just on the u, it shouldn't have been out front, so that should be inside the parentheses. There we go, that looks better. So now it's just a matter of plugging in. So we have 1/3 square root of 9 cubed plus the square root of 9 minus 1/3 square root of 1 cubed plus square root of 1. So we get 1/3. 9 cubed is, well, square root of 9 is 3, and then 3 cubed is 27, plus 3, minus, we'll have a 1/3, square root of 1 is 1, plus 1 is just 1, so it might be helpful to get all thirds here, so we'll have 27 over 3, plus 3 over 3, minus 1/3, minus 3/3, should turn back into, is that right? 26, did I get the 3 should be 9/3 if I could do some basic math here. 3 is 9/3, and so now when we do this, we have 27 plus 9 is 36, minus 4 is 32/3, and that looks good. So this one, the setting up that initial arc length was the same as before. That was new, more different than the last one. Where we went from there took a little bit more work, but remember, we started off the same way. We said, well, let's find the derivative of that equation. Let's square that derivative, and then we're going to plug into the square root. That is exactly the same. Setting these arc lengths up should be very formulaic. It is the same every single time. Now, solving the integral might be a little bit of work, as it was in this case. We had to start by factoring off that 1/4, and then we realized that we could write everything over the common denominator, and then we could factor the numerator into a perfect square so we could pull it out, and then we had to use a little u substitution. So this was a much more problem in the integration step. Finding the arc length was no different than the last one. Arc length is very, very formulaic. We just need to know that formula, and we're doing the same thing every single time.